So I'm Hesham. I'm a postdoc at Gert's lab at UCSD. So what I'll be talking about is an alternative learning mechanism for supervised learning in multi-layer networks that tries to avoid some of the issues of learning using standard backprop, issues related both to biological plausibility as well as hardware implementation efficiency issues. So first, a quick recap of the operations involved in standard supervised learning using backprop in multi-layer networks. So you have a network with a layered structure, and you feed the input, in this case x, at the bottom, and this is transformed through using the weight matrices, in this case W1, W2, and W3, across many layers in order to obtain the hidden activations H1, H2, and the output activation Y. Then you define an error function on this Y that measures how far it is from the desired output. And after you have defined this error function, you begin pushing the error back down the layer stack using the same weights that have been used during the forward pass. And by doing that, you in effect doing gradient descent in order to minimize the error. And after you have pushed the errors back down, then you can begin updating the weights using an outer product between the errors calculated in the backward pass and the activations that have been calculated in the forward pass. So many concerns can be raised against this standard view of backprop. The first set of issues is related to biological plausibility, and the most immediate concern here is the requirement for weight symmetry. So for this to work, you need symmetric weights in the forward and the backward pass, and we're not fully aware of a synaptic weight coupling mechanism in biology that can ensure that this is the case. The second problem is that you need precise interleaving of the forward and the backward pass. So you need something like a clock-like alternation between these two passes that hints at some form of global controller that's not very satisfying from the biological point of view. Another set of issues is related to hardware implementation efficiency. The first issue is that you need to buffer the network activations during the forward pass. And you need to do that because you need to keep them available so that you can use them to update the weights in the backward pass. And this is a significant memory overhead, especially in deep, large networks. The second hardware-related issue is that you need double weight lookup. You need to look up each weight twice, once during the forward pass in order to calculate the activation and the output, and once during the backward pass to do the error pushing down the layer stack and also to update the weight. And in practical large-scale networks, you typically have these weights stored outside your compute device in something like a DRAM, for example. And this double weight lookup is a significant, weight lookup is a significant portion of energy consumption because this is a step where you have to go outside your compute device to extend a DRAM to fetch the weights in. So the first issue, the weight symmetry, has been the focus of attention for the past couple of years, and a bunch of algorithms have come up that try to basically avoid this issue. These are the feedback alignment methods by Lookup and also by Knockland, the direct feedback alignment method. So this is very similar to backprop, but instead of pushing the weights down using a symmetric version of the weights used during the forward pass, you use random matrices, in this case B2 and B1, to push the errors back down. So you have two variants. You have the feedback alignment, the original version, where you push the errors down layer by layer, and you have the direct feedback alignment method that Emil talked about, in which you project the error from the top layer directly to the hidden layer using random matrices. So this gets rid of one of the issues, but it leaves the other three issues unsolved. Of course, you might have other issues with backprop, but at least this set of issues that I've mentioned are the ones that are relevant here, and these are the issues we try to address. So we come up with a technique in order to try to avoid these issues while learning in multi-layer networks. The technique is pretty simple. So for each hidden layer, you attach an auxiliary random classifier. So shown here is hidden layer I, and you take the activation HI of this hidden layer and you project it to a random matrix MI, in order to obtain the auxiliary classifier output SI. And then you define an error function on this SI, that could be, for example, cross-entropy loss or the hinge loss. In order to obtain the error EI at this local classifier, you project this error back to another random matrix KI, and then this projected back error EHI is the error that you use to update the weight using this equation, an outer product between the input activation and the error. So the error is here calculated locally for each layer. So this is done independently for each layer. Shown here is 2 layers. And these are the details of how this is done exactly. So you have HI and HI dash. These are the normal activations and activation derivative of layer I. Sigma is a nonlinearity. And you take this activation HI, project it using the random matrix MI to obtain the classifier output SI, and then you define an error E on this SI, and you get its derivative. And this derivative defines the error at the classifier EI, and then you project it back through KI. And you need to do an element-wise multiplication with HI dash. HI dash is a derivative of the hidden layer activation, and then you can use the result EHI in order to update the weights. So those of you who are familiar with the deep learning literature will see this is slightly related to deeply supervised nets, as well as the old work done on inception architectures. So in these previous approaches, they also use auxiliary classifiers in a deep network. But there are 2 fundamental differences. Here we use these auxiliary classifiers as a sole and only source of errors. In previous approaches, they use this to augment the errors coming from the top layer. Here we only use these auxiliary classifiers as error sources. We do not depend on anything that's coming from higher layers. The second major difference is that the parameters of the local classifier, in this case, for example, MI and MI+1, they are random and fixed. And this is absolutely crucial for the hardware efficiency of this approach. And I'll explain why in a minute. But if you choose Ki to be equal to Mi transpose, then what you'll be doing is practically gradient descent in order to minimize the local classifier error EI with respect to the layer parameters Wi. The forward propagation matrix Mi and Ki are fixed, and they are random. And we do that in order to be able to generate these weight matrices on the fly and cheaply using pseudo-random number generator. So by doing that, we basically make the memory requirement needed to maintain this auxiliary classifier parameter. The memory requirements are practically 0, because you only need to store the pseudo-random number generator seed. You need them random, but you need them repeatable. So you have to keep the seed of the pseudo-random number generator. But I mean, in the grand scheme of things, the size of this seed is practically negligible. So this is a more attractive hypothesis for learning in multi-layer networks from the biological plausibility point of view, because you get local errors that are available quickly to the hidden layer, and errors can be available while the input HI-1 is still exerting some effect on the hidden layer. So you only have a disynaptic error pass. You have a projection MI and a projection KI in order to quickly get the error. And as I will show in a few slides, you do not need MI and KI to be exactly symmetric, so you also do not have the weight symmetry constraint. But what exactly does this buy us in terms of hardware efficiency? The answer is it buys us a significant reduction in memory access overhead. So shown here is a pretty standard scenario if you are doing learning on custom hardware accelerators or even on CPUs or GPUs. You typically have a compute device whose onboard or on-chip memory is not enough to store the activations of the network and is not enough to store all the parameters of the network. So you would typically have a situation like that. You would, for example, if you're evaluating the forward pass in a deep network, you will have the activations of layer I-1, in this case AI-1 going in. You're fetching the parameters PI from external memory, in order to calculate the activation of the next layer, AI. And you have to write these activations back into external memory because you will need them later during a backprop. And you keep doing this process during the forward pass. And during the backward pass, as soon as you have the error EI+1 from layer I+1, you have to fetch the activations AI again from external memory, and you have to fetch the parameters PI+1 in order to execute the backward step to obtain the error at the previous layer EI, and also to be able to write back the updated parameters PI+1. The picture is quite different if you're learning using local errors. So again, you take the activations AI-1 from the layer I-1, get it into your compute device. You fetch the parameters for layer I, in this case PI, and you calculate the activation of the next layer AI. And directly from this activation AI, you can, using pseudo random number generator, quickly and without memory overhead, get the output from the local auxiliary classifier and use this output together with the classifier, local classifier error to obtain the required weight update. And then you can write back directly the updated weight matrix to external memory. So there's no explicit backward pass. And if you do the calculations, these are the memory read size or the memory read volume you need for a single, for learning on one example. In the backprop case, you need to fetch the parameters of each layer twice, and you also need to fetch the activation of each layer from external memory. But if you are learning using local errors, you only need to fetch the parameter of each layer once. Same goes for memory write. You reduce the memory write volume. And in terms of MAC operations, it's not, usually local errors would require less MAC operations compared to learning using backprop. It depends basically on the number of classes C. So Ri is the fan out of each neuron in layer I. So this is basically the number of neurons in layer I+1 that receive input from a single neuron in layer I. And this is typically a large number. So in, let's say, for example, MNIST or CFAR10 or CFAR100 even, you typically have C much less than Ri. So in the end, you would have the number of MAC operations needed for learning using local errors less than the number of MAC operations you need during backprop. But this is just icing on the cake. The main advantage is that you reduce the number or the volume of memory traffic. And this is really key because if you develop neuromorphic chips or hardware accelerators for deep learning hardware, computing is very cheap. What kills your power efficiency is having to move data around between memory and the compute device. So we quantified the accuracy of this local error, learning using local error method on a number of benchmarks. We start with MNIST because it's the simplest. And our first evaluation was in a layer of three fully connected layers with 1,000 neurons each. So this is using rectified linear units, using batch normalization, using dropout, all the usual techniques from deep learning. And learning using local error, this is the first column here, gives you an error of 1.27 at the deepest layer. So you see the error is improving as you go deeper in this case. And it also hints at another feature of this method is that you can get a classification result from each layer in your deep network. So the results shown here for the local error learning, each number is the accuracy of the random local classifier associated with each layer. We also, this in the case where you have weight symmetry, where you have Ki, which is the feedback weights of the local classifier, being a symmetric copy of the Mi, which are the feed-forward weights of the local classifier. We relaxed this requirement and only enforce sign concordance, so that corresponding entries in Ki and Mi, we just require that they have the same sign. They can have different magnitudes, only the sign needs to remain in line. And this leads to a slightly worse performance. We experimented also with learning using feedback alignment method, and this leads to significantly worse results than the results we obtain with local error learning. And in this, at least the results we obtain are on par with the results you would obtain using standard backprop learning. The third column here is for local error learning with trainable MI. This is a no-go in terms of hardware implementation, because if you have MI trainable, then you basically have to store them in memory. You cannot depend on having them generated using a pseudo-random number generator. We only include these results to get a sense of what will happen if we also allow MI to be trainable, but in terms of hardware implementation, this is not a route you want to take, because this would imply that you need to allocate memory for these extra auxiliary classifier parameters. Next, we looked at CFAR10, and we used a more complicated network. It's a network with 3 convolutional layers. First layer has 96 feature maps, second has 128, third has 256. And these are the kernel sizes, and the 3 convolutional layers are followed by 2 fully connected layers. And we use 2x2 max pooling after each convolutional layer, and we feed the local classifier for each convolutional layer from after the pooling. So we give the local classifier the post-pooling activations. So here the situation is different. Our approach, the local error learning, achieves 18.15% error rate, which is higher than backprop. And the performance deteriorates also if you if you dispense with the weight symmetry requirement and only keep the sign concordance requirement. But we're still doing significantly better than learning using feedback alignment methods. The take-home message here is that this gives you significantly reduced memory access, but as Emre mentioned in his talk, backprop is really it's the optimal algorithm for this kind of problems, but you have to pay the price in terms of extra memory communication overhead. So in summary, learning using local errors, it gives you a significant reduction in memory access in large-scale networks, which is useful if you are doing online learning on a power-constrained device. Another advantage is that classification decisions can be obtained from every layer in the network, unlike learning using backprop, where you have to wait until you get to the top layer in order to get your result. So this could be useful in situations where you need to dynamically balance power delay constraints against accuracy. So if you are delay constraint or power constraint, you can just evaluate the initial part of the network and get the classification result from the early layers. They're not going to be as good as higher layer classification results. For example, here is the classification accuracy gets progressively better as you go down the convolutional layers, but you can get them quickly without having to wait to evaluate the entire network. And of course, local random classifiers, they don't incur any extra memory overhead, since they can be cheaply and reproducibly generated on the fly using a pseudo-random number generator. And we outperform feedback alignment learning techniques in all the networks we have tried. But for complex data set, we still lag behind standard backprop, and we do not really expect this to change anytime soon. I mean, this is a technique that gives you more efficient learning in terms of memory access and power, if you are not dead set on having the best accuracy in your learning scenario. Yeah, that's all. Thanks. Questions?
Fabulous work, Hesham. Question on parallelization. Mm-hmm. Can the local classifiers run asynchronously, and how does your method compare with synthetic gradient?
The local classifiers can run asynchronously. So there are 2 ways you can do it. You can train the layers one by one because you don't get anything from the layer above. Or actually the method I used was I was running them, basically they are learning concurrently. So each layer is learning concurrently with the other layers. And during your second question is related to synthetic gradients and decoupled neural interface. So I think decoupled neural interface is, problem is that it introduces extra parameters and extra computational overhead. So what synthetic gradient buys you is that it allows each layer to learn independently of the other. So it's good for parallelization, but in terms of memory size needed to store the parameter, it's bad because you introduce extra parameters. It's also bad because you still expect things to arrive from the higher layers in order to train the local error predictor in your layer. So in terms of efficiency, this is definitely more efficient. The question, of course, is accuracy, and you have to find the right trade-off to decide which method is better.
So I'm going to ask you a question, but I want maybe save the answer till the discussion section after William's talk, because I think it's something for everyone on the panel. You talked a lot about the motivation is hardware efficiency.
And biological plausibility.
And then the biological plausibility. And that's what I want to ask about. Deep learning is, as a neuroscientist, so far away from neuroscience to begin with. Why should biological plausibility be a constraint at all? So I don't know if you have an answer now or if you want to, maybe as a discussion point. I think Emery's mentioned something similar in his talk. So.
Yeah, maybe I can give a quick answer. Yeah. I mean, you find that once you constrain yourself to be more biologically plausible, you automatically become more hardware efficient. Because, I mean, for biological plausibility, you need local learning rules. You need something that's robust to noise. You need, for example, limited weight precision. And automatically, by thinking along this direction, you end up with a more hardware efficient algorithm. So it's not a matter of constraining myself, it's just a way of thinking that automatically leads to more hardware-friendly solutions. Thanks.
Thank you.